Hello. Ooh,
Hello.
wow. Maybe if I speak from here, that'll work.
Well, I have to
Hello.
be careful too.
Hello, hello.
The other way around.
Yeah,
Not too far, we can hear 'em.
right. How's this? Does this sound okay? Okay. All right. Today I want to talk about some insights available to me from having read 3 books specifically that I'll call out, having written a book, and also just things I've picked up along the way from science educators and communicators and whatnot, about the idea of certainty and science. And I thought it would be fun to talk about, revisit this issue about the height of Mount Everest. You may recall from a couple months ago I was talking about what's the tallest mountain on Earth as part of a talk about scientific misconceptions. And if we have enough time today, I've got another little, after this talk, I've got a little blurb about another misconception that I recently corrected in my own corpus of knowledge, and I thought you might find fun also. Anyway, how tall is Mount Everest? So, everybody knows, right? It is 29,003 feet. Do I have another taker? 29,031 feet. Going. Sold for 29,031 feet. So the difference between 29,003 and 29,031 is, I don't know, 27, something like that. So not very big. And the measurement of the height of Mount Everest has changed over time from the 1960s when it was first performed until the modern era of GPS satellites and so on. We've had all kinds of published heights of Mount Everest in geographic magazines and in data tables. The height of Mount Everest, if you plot the published accepted value over time, it's kind of going, but the mountain isn't changing that much, right? So that highlights, among other things, the difficulty of measuring. Also, the units that we use to measure, or the specificity with which we measure. How tall is Mount Everest measured in angstroms, which is about the size of an atom? Really big, right? But I don't know that anybody, you could probably ask one of the chatbots these days to tell you how tall is Mount Everest in angstroms. But I guarantee you, if you got that answer from 29,031 feet, the answer would be wrong. For a couple of reasons. One of which is that Mount Everest is changing over time. So the Indian subcontinent is crashing up against the Asian continent, and there are earthquakes and uplifts and subductions and all kinds of interesting plate tectonics and geologic phenomena occurring around the Himalaya, whatever your preference there, mountains. So on average, Mount Everest grows by about 1.5 centimeters a year. Gets taller, right? So you give it a decade, and that's, almost half a foot, right? So maybe it'll be 29,032 feet within our lifetimes. Or maybe there'll be an earthquake, and it'll subsist a little bit. There's also erosion happening at the same time, right? So you got these competing forces. But not only that, it's walking northeast. Mount Everest is walking northeast at about, I think it was about 3 inches a year. So Mount Everest is on the move. And then there are these tidal effects. The tides cause the water around the earth to bulge out, right? Well, it also causes the land to bulge a little bit. So there are tidal effects that change the distance from the tip of Mount Everest to the geometric center of the Earth as tides wax and wane. I mean, we don't really talk about that much. So what's the height of Mount Everest? I don't know. It's big.
I'm not planning on climbing it anyway.
Yeah, you don't want to climb it anyway, right? Who would? Yeah. So the point is that something like 29,030 feet, or 29,000. For much of my life, until I searched the mountain topic that I talked about a few months ago, in my own head, I had 29,028 feet. That was the value I had remembered from, I don't know, maybe the 70s. But turns out it's 29,031 is the current accepted value. And that gets into precision. Is it okay to say that Mount Everest is about 5 miles tall? Sure. Is it okay to say Mount Everest is about 29,000 feet tall? Sure. Right? So the specificity with which we measure or recount the results of a measurement can change depending upon the relevant context. If Mount Everest changes its height by a couple of centimeters a year, does that mean it's no longer the tallest mountain in the world? No, right? There was a bit of a hubbub a few years ago about Mount Everest versus K2, and which one is really the tallest? Well, Mount Everest ended up coming out head and shoulders ahead of that one. So it's still the tallest mountain on Earth, even if it's changing a little bit. But it may not be that way in 5 or 10 million years. So also some of our measurements are relevant to a point in time. When was the measurement made? What were the contexts relevant to that measurement? All right. Another similar circumstance involves the world's tallest tree. Right now it's recognized as Hyperion. But over the past couple of decades, the world's tallest tree has moved around a lot more than Everest. Well, the tree itself hasn't moved, but the designation of the world's tallest tree has come and gone from different trees over the past couple of decades. Right now, it's recognized that the tree Hyperion, a giant sequoia redwood, is the tallest tree on Earth. But there are also trees in China and Africa and other places. If you look at Wikipedia to see the tallest trees on Earth, they're not all giant Pacific redwoods. And trees are growing. So maybe that's going to change. And this is related to a book. The first book I read about this topic is a wonderful little tome that makes one have some nice philosophical thoughts about science and measurements and how we convey facts and do science, called The Half-Life of Facts. I'll have an image of that book at the end of my presentation, so you'll be able to see it. So when talking about some of these topics, we often confuse the concepts of precision and accuracy. If you hit the target, you're accurate, give or take. If you hit the same spot over and over again, you're really precise. I mean, the target could be there, and you could be throwing your darts over there, but, precision is available to you whether or not you hit the target. So here's an example of that. This is an illustration I made for my book. So figure A is you're fairly accurate. All of your darts cluster around the center, but the clustering is sort of open and dispersed. Figure B, you're very precise. You can throw that dart and hit pretty much the same spot over and over and over again. Figure D shows that you are neither accurate nor precise, because your darts are spread out all over the place and they don't center on the center of the target, the bullseye. And then ideally you've got the situation in C where you're both accurate and precise. Yeah.
In analytical chemistry, we utilize this a lot. We look for precision, and the moment you have something that is precise, you then calibrate accuracy. So, for instance, with a spectrometer, you're looking for exactly the same point, exactly the same point, exactly the same point, and then you adjust so that it's on target.
But you know the target in advance.
Yeah, because again, we look it up in the book.
Right.
I remember from my Boy Scout days, if you got a grouping like shown in B, it actually moved. It might be because your rifle was
Your sights were
the
off.
sights are off,
Yeah.
and they'd move the target to compensate.
Or move your sight. You adjust your
Well,
sight.
yeah, you could adjust
That's
the
what
sight.
Joanne's talking about. If you end up with something like B and you already know where the center or where the correct result is, then you adjust your mechanism, maybe the sight, maybe the apparatus you're using, to make sure that that tight, precise clustering indeed looks more like image C. Right? So precision and accuracy are relevant concepts. And some things that we measure, we have really significant variation in both the accuracy and essentially no precision. Right? I want to talk about the idea of proof. So one of the things that often comes up in conversations, especially conversations that science-minded people have with people who don't have that same metaphysical preference in terms of the way they think about the world, is the concept of proof. Can you prove that global warming is happening? Can you prove it? Right? Can you prove one that I engage in occasionally is, can you prove there's a God? Can you prove there's no God? Right? That's a common one in social media circles. Well, in logic and mathematics, there is a concept called proof. And that concept is related to what's called deductive logic. And in deductive logic, you start with a few premises, or what are they called in geometry? Axioms, thank you. You start with some premises or axioms, and they're just accepted as true. A line is the shortest distance between 2 points, right? Etc. And building upon that foundation of axiomatic truths, you can extrapolate other true statements, sometimes up to the level of mind-boggling complexity, like the 4-color problem for coloring in a map. What's the minimum number of colors needed to color in any arbitrary map so that you don't have to have any 2 colors side by side for 2 different regions? And the minimum number is 4. It took decades and decades and decades for mathematicians to prove that. And that kind of proof is, pardon me, bulletproof. It is an axiomatically oriented and derived deductive proof of a conjecture in logic or mathematics. We don't do that in science, right? Science especially physics, borrows liberally from mathematics. It turns out when you're making models of the way the universe works, that mathematical models tend to be some of the most wonderful ways we have of characterizing and capturing behaviors within our cosmos, especially behaviors that result in measurable things, distances, intervals of time, amounts of stuff, geometric relations between stuff. So mathematics is really relevant to the sciences. How many people in your sample population are undergraduates? How many are senior citizens? How many males do you have? How many females do you have? Countable things. And often in social science studies, they'll introduce what are called dummy variables, right? To stand in numerically for a trait. Like maybe blondes are a 5, redheads are a 4, brunettes are a 3, dark brown hair is a 2, and black hair is a 1. I'm just making that up off the top of my head, but by substituting these kinds of variables for different shades of hair color, melanin content in your hair, you can maybe come up with some scientific laws about that. And I'm going to talk specifically about the notion of scientific law in just a moment. But anyway, deductive reasoning, mathematical, logical kinds of proof are not available when talking about science and the natural world. And because they're not available to us in the same semantic, definitional kind of way that they are for mathematics and logic, scientists and science communicators often back themselves into a corner that other people exploit by saying, well, I can't prove that the earth is round. What do you mean you can't prove that the earth is round? Well, I can't start from fundamental axiomatic principles and derive, a completely different milieu of making statements that have credibility, confidence, and certainty. And that causes some problems. This is a picture of a mathematician. I tried to pick a famous one. This is Carl Friedrich Gauss, one of the most famous mathematicians. There are many others. I thought about asking you all how many mathematicians you can think of, and I'm not gonna do that. But Subramanian, he had a movie come out about the Indian mathematician Subramanian, who had such gifts to just with number theory. Anyway, I don't want to go down that rabbit hole. It's a wonderful rabbit hole, but we have other places to go today. All right, and then we have what are called inductive evidence. That's when, well, first of all, we have this new word, evidence. So in deductive reasoning, you don't need evidence, you just need axioms and rules. Rules about how to put those axioms together in new and hopefully clever ways. But when dealing with the natural world, we use inductive reasoning based on evidence. We don't deduce, we induce. And that is, well, I've measured 547,321 swans, and they're all white. Therefore, all swans are white. Right?
Close.
Close. Right? Then there's the black. Who asked for that? A black swan. Right? So when making scientific pronouncements, we can say nearly every swan you're likely to encounter in the world is white. And that's the kind of language that scientists use for almost everything. And I think that that can be problematic. Because of the common parlance we use when talking with people, talking with other human beings, especially human beings who aren't scientifically oriented or particularly educated about scientific vocabulary, say, well, it's plausible, or it's very likely, or we're fairly confident, or we're very confident, or the consensus is. People find wiggle room in all those statements. Well, if that's the consensus, there have to be non-consenters, right? Yeah, right. It's one of the ways science works, okay? But I think sometimes we're too timid, and we temporize too much about things for which we have unassailable certainty. I could say nearly unassailable certainty, because there's always that little part of your brain that says, well, we could change our mind. I mean, if we were to find an electron that doesn't have the standard electric charge associated with an electron, if we were to find an electron that had 18 times that amount of charge, that would be a stupendous discovery, and contrary to everything we think we know about the way the universe works vis-a-vis electrons. Muons are electrons that have a higher mass, not higher electric charge. But in any case, we always, as scientifically minded people, we always have to be open to the possibility that something could change our mind. That was one of the presentations I gave about Mount Everest earlier, was changing your mind about things you think you know. So that wiggle room is often exaggerated, I think. We can say we're confident, or science has developed a consensus that the following is a fact. Right? We can say things like that that kind of try to get rid of some of that wiggle that other people try to exploit. All right.
Scott,
Yeah.
would you suggest the word scientific fact?
Yes, I'm going to get to that. So this is a vocabulary issue. I don't have any credibility or notoriety or influence, but I've found it useful when thinking about nature and science and the relationship between them to distinguish between what I call natural laws and scientific laws. Scientific laws are the models we make to understand, describe, and predict things about the world. Those are scientific laws. Scientific laws are a human construct, always. Natural law just exists. Gravity exists. The law of gravitation is a real thing. It used to be that we modeled the law, the natural law of gravitation, with Newton's equations describing gravity and gravitational forces. Now we have an even better model, and that's called Einstein's general relativity. So the scientific laws about gravity have changed over time and are likely to change in the future. We know about some problems with Einstein's laws of gravity. But I think it is useful to distinguish between scientific laws or scientific confidence and facts versus natural law and natural facts. As far as we can tell, there are some things that are natural facts, and we know these things perfectly, like all electrons are the same. They may be oriented differently, but they're exactly the same. An electron here is the same as an electron in a galaxy near the beginning of the universe. All right. So talking about scientific consensus, this is July 4th, 2012, when a last big piece of what's known as the Standard Model of Particle Physics fell into place. This, there had been a prediction since the, I believe, 1960s, maybe early 70s. There had been a prediction that electrons, protons, neutrons, photons, and several other particles you may or may not be familiar with, all of these particles, and the particle zoo that constitutes what matter can manifest in our universe, scientists were very confident that they had discovered all of the ones that fit into this particular model, this explanatory model for how particles and forces and the particles that convey forces in the universe, how all of those are put together, except for one. And that was called the Higgs particle. It's a really subtle and wonderful insight into nature, which is things have mass. Electrons have mass. Protons have mass. Your house and your car have mass. You may have more or less mass, depending. Right? Why? Why mass? I could probably give, and maybe next year I will, give a whole talk on this topic again. But whenever you have a phenomena in nature, one of the questions you can ask is, why this? Why does this happen? Is there a deeper reason? And one of the deeper reasons for the existence of mass is that fundamental particles that constitute everything we see, those fundamental particles have an interaction with what's called a Higgs field. It gives different particles different masses. And so they thought, well, if there's a field called the Higgs field, every field has to have a particle. This is the way modern particle science and quantum mechanics works. So they hypothesized the Higgs particle. In 2012, July 4th, they announced it. But the cool part of this that I really want to emphasize is, you see this room of people? These are the people whose names appeared on the papers talking about the discovery. Do you know who discovered Faraday's law? Anybody, any guesses? Faraday, right. Do you know who discovered the Higgs particle? All those people, right? So, as our knowledge about the natural world has improved over the centuries that we've been at this formal practice of science, the amount of effort and money and precision and skill required to suss out ever more fine-grained details about the way the universe works, whether it regards gravity and black holes or submicroscopic particles, the amount of effort that goes into that is exponentially increasing. There's still a possibility that somebody working in their garage could invent some completely new thing that turns our understanding of nature on its head. That possibility, however, if you were to write it as a number, is probably got something like 80 zeros, 80 zeros before a 1, right? We always have to be open to the possibility that we must be compelled to change our mind because of evidence. But that doesn't mean we can't be confident about the things that have incredibly high certainty. Certainty so high that I think it's perfectly fine to say they're scientific facts. The way I represent this in my book, and I've used this diagram probably 10 or 20 times in science talks over the decade or so, is this special curve called an asymptote, an asymptotic curve. The asymptote's actually a line that it approaches, but this is an asymptotic curve. It may kind of look like a parabola. Those of you who are familiar with, remember high school analytic geometry. But the red line indicates our scientific knowledge. It could be our scientific knowledge about the metabolic processes entailed in the way Alzheimer's disease works. It could be our understanding of the way electrons behave in atoms. It could be whether or not margarine or butter is better or worse for you as a part of your diet. And for each of these things that I've mentioned, you could probably pick a point along this red curve and sort of intuitively figure out, are we close to a perfect description of reality regarding that particular claim, or are we relatively farther from it? Think about the way scientific knowledge evolves over time. One of the good examples that we can all recall in our recent lifetime history is COVID. Remember when the guidance from scientists, I shouldn't put that in quotes, they were actual scientists doing the best they could when this disease first started spreading. They would say things like, it's not transmitted through the air, right? And eventually, that guidance changed. Scientists studying the disease and its vectors, its methods of transmission, they changed their mind. But they didn't change their mind capriciously. Not to the point where they should be criminally prosecuted or politically persecuted. They changed their mind because they got more evidence, right? When you're in the early stages of investigating something, one of the things that I talk about in my book is you go through a stage called stamp collecting. Oh, this thing looks like this other thing. Let's group it over here. Oh, this thing looks very different. Let's put it over here, right? Linnaean classification of species, right? Oh, well, this is a quadruped. Well, this is also a quadruped. You've put a lizard, a bird, and a rhinoceros in the same category. They all have 4 limbs, right? So, stamp collecting, this galaxy looks kind of like this galaxy. This galaxy has this pinwheel shape. Oh, look, here's a galaxy that just looks like a blob. All right, well, we'll make 2 different classifications of galaxies. Oh, well, this one looks kind of like a blob that's exploded, and this one looks kind of like a blob that's in a cigar shape. And this one looks like a spiral that's really tight, and this one looks like a spiral where it's just all flung out. Well, let's make some subcategories, right? So one of the phases that much of scientific modeling and analysis goes through is stamp collecting. One of these things is just like the other, right? Right? This is a necessary part of science. You group things together. You try to find commonalities. Then you try to find explanations for the commonalities and explanations for the differences. If you look at the elements in the column of a periodic table, they have similarities. They tend to react with the same other kinds of atoms, right? So things in a column in a periodic table tend to be similar to each other. And then you get the rare earths that are similar and they're not really in a column, and that's just weird. But our understanding of nature, we're on a hyperbolic curve is another name for it. We're on a hyperbolic path approaching an asymptotic perfection of a perfect model for understanding nature. And sometimes we're far away from perfection, especially as something gets really complex, like the human brain. The human brain is, as far as science knows, the most complex entity in the known universe. And we each have one. Isn't that incredible? And we fill it full of junk all the time. I don't know. But it's amazing that we can say anything about the brain, anything about psychology, or economics, or sociology, or other kinds of sciences that depend upon the way the brain works in different contexts. So there's experiment also versus observation. We can do experiments like the particle collider, where we smash bits of matter together and see what comes out the other end. We can do experiments with chemistry, we can do experiments with biology and medicine and fundamental physics. When's the last time you heard about an experiment in astrophysics? Right. Now, one of the things we can do is we can try to model what we believe. We have high confidence that we know what goes on in the center of a star. The chances of us ever being able to stick a thermometer into the center of a star is 0. Do you know why it's 0? It's not vanishingly small, it's 0. Because every thermometer, every measuring device, every observation device that we would try to put there is made out of molecules and atoms. And what happens to molecules when you try to put them in a star? They go, whee! And they're no longer a machine. So we will never, ever measure the core of a star. There's some wiggle room there with white dwarfs, which some say are the core of a star that's no longer undergoing fusion. I'm going to skip past that, just acknowledge that that objection may exist. So how do we have any freaking idea what happens in the core of stars? We can't see them, we can't measure them, we can't go there, we can't stick a probe in the center of a star. Well, one of the things we do is we use particle colliders. And we try to simulate the kinds of pressures and temperatures that we can extrapolate from scientific laws that we have a high confidence the kinds of temperatures and pressures that should exist at the center of a star. So we can make scientific claims about things we've never seen and never will see. Isn't that amazing? Right? Were you there? Were you there in the center of the star? How do you know that the core of a star is 15 million degrees Kelvin? Were you there? Did you measure it? Well, no. I mean, just the fact that you have to say no gives people a foothold in the door of skepticism. But you can say something else. You can say, every star that we observe behaves in a manner consistent with the fact that they are undergoing nuclear fusion under intense pressure and heat at their cores. If stars didn't behave according to that, stars would be much different than we see them. So this is the way stars work. We can say things like that, and we haven't hedged our bets. We haven't left room for equivocation, and we also haven't said anything scientifically wishy-washy, right? So we can be careful about the way we communicate with people when we're communicating things about knowledge science has gained vis-a-vis the real world. Observational science, the best one I know of, is astronomy and related astrophysics and cosmology. But there are others when we're trying to understand how an ecosystem works, right? Mostly that's about observation. Maybe there's some experiments you can do as an ecologist, but you don't really want to remove all of one species from an area deliberately just to see what will happen, right? You don't do a controlled experiment like that in most ecological contexts. So ecology is another observational field. Psychology is largely an observational field. You can try to put parameters around what you're doing. You do run psychology experiments, but it's really hard to control for all kinds of things like whether the person had breakfast, right, etc. But we know about some things. We know about optical illusions that are common to essentially every person tested, etc. I want to talk a little bit about uncertainty. You know, talking about wiggle room. One of the things that people who will argue about scientific claims will appeal to is the very notion of chaos and uncertainty and randomness. And when you really press, maybe they'll even bring up the Heisenberg uncertainty principle. Oh, that's at the bedrock of physics. Do you know how relevant that is to cats? It's not. It's not relevant to cats. So in our world comprised of quintillions and septillions of particles that constitute you and me and bicycles and stars, there are so many particles moving in so many different ways, shedding and gaining electrons and chemical bonds and so on and so forth, that we cannot hope to model those in exacting detail. So we make generalization, things like Boyle's law about pressure and forces, the ideal gas law, PV equals nRT. Pressure and volume is related to the number of particles and the temperature, right? So we make generalized laws, scientific laws, that capture bulk behavior. but they all have breaking points. You know, one of the things that the ideal gas law presumes that is almost never communicated? It presumes that particles are point-like, that they don't have physical extent. People have tried to make an analog, an analogous law for the ideal gas law, pretending that every particle is a sphere instead of a point. And I don't know, maybe Ray, maybe you know, or somebody else knows, I don't think anybody's been successful yet. You want to?
There's Biot-Savart's law, which, I mean, like the ideal gas law presumes that particles are not interacting with each other, too. And Biot-Savart assumes that they are exerting some forces on each other.
Okay.
Right. And which is, I mean, it is a generalization of the ideal gas law, right? The Biot-Savart's law simplifies down to the ideal gas law if you
Remove the
take a
interaction.
few certain constants to zero that
Okay.
model, that account for those interactions. Yeah.
So once again, we're on that asymptotic curve, right? The ideal gas law is pretty close to an accurate description of reality in many contexts. But Biot-Savart's law is a better one, but the context in which it becomes relevant may be limited enough that we don't have to apply it most of the time. The same thing happens between Newton's law of gravity and Einstein's law of gravity. We can shoot a space probe from here to Pluto, and the journey can take, I don't remember, 10 years, and it will arrive within a few meters of where we predicted it would arrive 10 years ago. And all we used to make that happen, with all kinds of slingshot effects and oblique orbits and whatnot, all we used to do that is Newton's equations, which were replaced and improved by Einstein's equations. But Einstein's equations are a complete muddle. It's really hard to deal with them. In fact, they don't even have what we would call, it's called an analytic solution, where you can write down a solution saying, this is where it'll be at time t. According to this starting condition, here's where it'll be at time t plus 10 years. There's no equation like that, rarely an equation like that comes out of the theory of general relativity. You have to do numerical simulations. And why would you waste all that supercomputer time when Newton's laws do a perfectly good job? Are Newton's laws correct? Interesting. Yes? No? In the context in which they are applicable, they are applicable. Right? So there's randomness and chaos due to our imperfect knowledge. It's called epistemic uncertainty. We don't know everything. We can't write down in an accounting book everything about what everything in a bottle of gas is doing. Randomness and chaos derive from epistemic uncertainty. Epistemology, theory of knowledge. And then there's inherent uncertainty, which is the Heisenberg uncertainty principle. And I'm not going to go into it deeply today, except to say the contexts for which that is relevant are so precisely controlled and typically minuscule that if anybody tries to throw that argument into a political discourse about climate change or people changing their mind or other kinds of phenomena that we can see with our eyes, in nearly every case, that'll be a specious argument. The uncertainty principle doesn't do the heavy lifting that people ask of it. All right. Speaking of the uncertainty principle, Einstein famously said that God does not play dice with the universe. Turns out he was wrong. And was it, Niels Bohr, was it Niels Bohr who said not only does he play dice, but he throws them where we can't see them?
Yeah.
Who said that? He might have said, might have been Feynman. I don't remember.
What I was remembering was him saying Einstein's not telling God what.
Yeah, Niels Bohr, thanks, Ray. Einstein said, or Niels Bohr told Einstein, Albert, stop telling God what to do. All right, I want to talk about credibility. So I can make an argument that no dragons exist and no dragons have ever existed. And I can make that argument with supreme confidence. Why? Anybody want to try to?
4 legs versus 6.
4 legs versus 6. 4 limbs versus 6. I've never, oh, the Komodo dragon. How many appendages does it have? 4. In the fossil record, how many times have we found vertebrate fossils that have more than 4 limbs? 0. Yeah, I mean, there are strange birth defects occasionally that happen. So you have to allow for some wiggle room. Biology is complex. Embryogenesis and fetal development are complex. But in terms of a species, a thriving species, a robust species that's more than just an individual example, we have never found a species that has more than 4 limbs.
We have to say thank you to Tiktaalik.
Tiktaalik, right? And the fish that we are all descended from. The fishes were descended from. So that's why I can claim that no dragons exist on Earth, and no dragons ever have existed on Earth, and it's not likely that any dragons will exist on Earth, albeit we do have gene editing, so I don't know, maybe those bets are off. But what's the plausibility that there could be dragons? Let's forget about the fire-breathing nonsense. What's the plausibility that there could be dragons on other planets that have had their own evolutionary histories? Much more plausible, right? So if you're going to write a story about dragons, please set it on another planet. And McCaffrey did that, right? Okay, so plausibility versus possibility. It's not plausible that we have dragons on this planet. It is plausible that there could be dragons on other planets. It's impossible that we would have an intelligent entity comprised of an ion cloud. Sometimes in science fiction, you come across these notions of an intelligent cloud, right? Clouds lack the structure and complexity to be able to elicit anything like the connectedness among network constituents that we see in computers and brains and certain funguses that work collectively together. So we've got all kinds of examples on Earth about what we might hand-waving call intelligence, but a cloud can't do it, right? So that's an impossibility. One of the things that's been ascendant in scientific literature and the philosophy of science for the past 20 years or so is something called Bayesian statistics, which is, I won't get into it right now, but it has formalized the notion of credence. And that's a wonderful word. Most people know what credence means: credibility, incredible, non-credible, right? So credence has acquired some mathematical trappings in Bayesian theory. And Bayes was in the 18th century, I think. So it's older from a mathematical standpoint, but it's been repurposed to deal with social sciences, etc. I tell you something that is not credible. What is not credible is a violation of the laws of nature. Not scientific laws, which could be maybe inaccurate, but the laws of nature are never violated. And our best knowledge, our best scientific knowledge about the laws of nature are also not violated, right? The speed of light is never exceeded. There was an Italian team in the opera experiment in 2011 that got a result that said some particles had moved faster than light. And when they published about it, they said, "What the hell is happening here? This shouldn't be possible." They actually said something like that in their paper, but it was, very formal. And other scientists joined in the analysis, and eventually they found a loose wire. And in fact, no particle had moved faster than light. They were honest about it when they published their finding. They did this experiment, they got this strange result, and they published it. the person who led that consortium of scientists who made that surprising claim was fired. That's unfortunate, because this is the way science should be done. If you do an experiment and you come up with a completely off-the-wall result, you should still tell people about it. Remember the cold fusion thing? They told people about it, but they didn't release any of their methodology. The people who did the opera experiment for the particles released their data, their methodology. They were exhaustively detailed about what they did and how they found what they found. The people who claimed, Fleischmann and Pons, who claimed cold fusion, said, we've got evidence of cold fusion, and we'll tell you more later, but they didn't. All right. So violating the laws of nature is not something that should ever be credible. Science is a social activity. There's problems with the way science is done in our culture. Publish or perish. The job you get, the pay you get may be tied to how many publications you've made. There have been all kinds of studies that show that when researchers cite other papers, there's a good reason to believe that most of the time all they've done is read the abstract of the other paper, and then they go on to cite it. There's some evidence to support the claim that some papers are cited without ever being read, even their abstract, because they're cited in a context that has no relevance to the paper that's being cited, right? So there's all kinds of shenanigans that go in there. There's human self-interest. The more I publish, the better job I get, the more bicycles I can buy for my family, whatever, right? So there's human self-interest. There's funding issues. How is funding doled out? By whom is it doled out? Who makes the decisions to dole it out? What kind of biases do they have? Are they pro-global warming? Are they anti-global warming, etc.? So the biases in the funding apparatus. The National Science Foundation has pulled funding about climate change research, even though it's highly credible science. Failures and follow-ups. A lot of failures are just not published, especially in psychology studies. Have you heard of p-hacking? How many of you have heard of p-hacking? Okay, here's an example of p-hacking. I think that drinking orange juice in the morning makes people more alert when they take a test in the afternoon. They'll do better on tests if they've had orange juice in the morning. I do a bunch of statistics gathering, and I try to account for everything. I've got women who do it, I've got men who do it, I've got younger and older people who do it, I've got people with modest IQs and below average IQs and above average IQs and on and on and on and on. I collect an exhaustive amount of data about the background and properties of all the people who drink orange juice and then take a test. And what I find is that there's no correlation between people who drink orange juice and take a test, unless they're 38-year-old redheaded women. Then I can publish and say that orange juice helps young women on tests.
Ta-da!
No, that's p-hacking. That's when you slice and dice your data set to such an extent that eventually, just by random chance, you find a correlation that doesn't imply a causation. P-hacking is common. It's too common in the social sciences and psychological sciences. Okay, for this next part, I want to demonstrate something. Joanne, could you come up here? Mike? This next part is kind of tough, so I need to prepare for it. I need to psychologically gird my loins. Mike? All right, let's do this. So there's a study that came out a few years ago that said, if you pose like a superhero before an important meeting or discussion, you're more likely to be persuasive and successful. All right, how many of you saw that article or read about it? It was a splashy headline, wasn't it? I thought about, why didn't Saturday Night Live do what we just did, make a skit? You know, a bunch of politicians behind the stage of different parties. You know, there's Mitt Romney, and there's George Bush, and there's Jimmy Carter, and they're all back there just... Right? Yeah. Right? Why don't they do that? Yeah, thank you. So some of you saw that study. How many of you saw the retraction of that study? Nobody. Splashy headlines about, remember Carl Sagan's adage, extraordinary claims require extraordinary evidence. Remember that? Yep. Well, we see extraordinary claims all the time, and they're not accompanied by extraordinary evidence. There was a similar story about NPR. I heard about it on NPR. The story wasn't from NPR. Some researchers found that if you sent a woman who'd had an abortion around to canvass politically to talk about abortion, and you did this in conservative neighborhoods, the very fact that people in a conservative neighborhood were talking to a woman about abortion who had had an abortion and could talk to her about why she made that important life choice, the very fact that that happened was claimed to be persuasive, that it flipped some opinions and votes. I thought that was incredible. Turns out it's not true. Which makes me a little sad. It would be great if it were true. What is true is that if you engage in a conversation with people, whether or not you're a person who had that event happen, so this particular study was about trans people. If you have people who are empathetic and sympathetic and progressive about trans rights, talk to conservatives about what's relevant in terms of trans rights, there's about a 1 in 10 chance that you'll change somebody's mind just by talking to them, engaging with them, and being sympathetic about the issue. Thinking Fast and Slow, the book by Kahneman, very popular science book. He eventually won a Nobel Prize, or I think he did before the book came out. But the idea is that one of the big things in his book is priming. Judges who hand down parole decisions before lunch are less likely to grant parole than the same judges handing down parole decisions after lunch. Hungry judges are mean. Right? That's the conclusion. However, when they went back and analyzed the data, what they found is that the difficult cases had been scheduled at different times throughout the day. The cases that were essentially slam dunks, yeah, parole, who cares? You know, you're a nonviolent offender, et cetera, et cetera. So it had more to do with scheduling than with hunger pangs.
I remember hearing, now I don't know how valid it is, but I remember hearing that they went and that some food industry group went and asked a bunch of doctors, is it important to have a hearty breakfast to start the day? And of course, all the doctors said yes. And then the food industry went ahead and defined a hearty breakfast.
Oh, wow, right, yeah. Yeah, it doesn't involve granola bars and plenty of fruit. It's, all the bacon you can eat. Yeah.
Oh, when I was a kid, it was fruit, cereal, milk, bread, and butter.
Yeah, sure. All right, I'm running out of time here. Let me get through a couple more slides. TED Talks, The Power of Posing. I talked about that. She had millions of views in her TED Talk about the power of powerful posing. Right? Debunked. Right? Hungry judges. I talked about that. Speaking of debunking, in my last talk about Mars, I put up these values for the amount to build a space station in different contexts. Around the Earth, 2.5 million. On the Moon, 25 million. And on Mars, 250 million. That's the way I said it. I misspoke. This is the cost to put 1 ton of material at these locations.
Oh, wow.
Yeah, so I'm sorry, I made a mistake. So being able to admit that you made mistakes, being able that you don't know something, being able to say that your data doesn't support a particular hypothesis, those are all very important parts of scientific humility. The reproducibility problem, our system is not built to be able to financially support scientists who want to go and reproduce a questionable study like the Milgram prison experiment and many others. But there are groups out there, and more so in the past 20 years, that are focused on finding fudged data. There's this an anesthesiologist from London, from England, who has been responsible for finding all kinds of fudged data, and he's gotten professors fired. That's not been his goal. His goal is to help us do good science. All right. So there are ways to keep science safe. One of them is the notion of peer review, which is moderately effective, replication, somewhat effective, meta-analysis, looking at studies of studies, fraud and forensics, data auditing, like the anesthesiologist does. You know, there's a reason to be proud of what we've done, what we've found out about nature, but let's not be arrogant about it. One of the aspects of the scientific disposition that is very important is humility. Humility before nature, humility before our peers, humility that something could come out of left field that's worth considering. So we know an astonishingly huge amount about nature. Compare us to people who lived 1,000 years ago, whose best recourse to explain many natural phenomena was magic. There's no real room for magic anymore, which disappoints many people. It would be cool to live in a world of magic. I love reading books about magic. But science has been pushing the credibility of magic further and further away from plausibility, to the point where I don't think magic is a plausible explanation anymore. It doesn't mean that we're not discovering new things. We're discovering that the early baby universe, after the Big Bang, but before things we can see as fully formed galaxies, James Webb Telescope is showing us that the early universe is much different than we thought or predicted it would be. And that's cool. Here's 3 of the books I used to inform this talk. So feel free to take pictures, whatnot. Sorry I ran over by about 4 minutes. But thank you for listening to a talk about credibility and science.
Yay.